Good morning, guys. This recording is a follow-up for problem 113 from chapter 17. I know I told you guys that there was some work in it, and actually when we were doing it live with the other problems, we ran into a problem with the algebra, in a sense that I actually was able to fix that, at least through the before uploading it back onto Canvas, and I pointed exactly where the error was. So let's go through that, fix the problem, and basically come up with probably a better way of doing that same relationship between this is basically between how far we are on the shape there, on the plug, basically with respect to the radius of what it is. So basically here is the shape, if you guys don't remember. So what we have in here, what looks like a plug. I exaggerate the shape here a little bit, I know. So think of this one of some sort of, for example, you have a big thermos, a huge thermos, and you have a plug to seal it, where the thermos probably is made up with a reflecting metal outside, and probably the inside has some sort of a plastic, glass structure. And between the two, there is probably perfect insulation. For example, there is no air in there; it's completely vacuum sealed. And then what happened in this case, you pour your coffee, for example, or you put your super cold drink, for example. Let's say, for example, at 0 degrees Celsius with ice and all of that. And now you put the plug on top of everything. Now the plug has conductivity K, so in this case, it's going to basically start to. So the outside is here, sitting at a temperature TH, and the inside of it is sitting at a temperature T cold. So in this case, the heat is going to come from the outside to the inside at the rate of H. So H in this case is the heat current that is flowing through conduction, okay, between the outside and the inside, and of course it's heating the inside. So let's say, for example, after 5 minutes, you open the plug, you measure the temperature inside, and you see that the temperature went a little bit up. You can measure the heat that went in, Q. Q in this case will simply be equal to the mass of the liquid that you have in there. Let's say, for example, we have 1 liter, which is a kilogram, times the specific heat. Let's make it water, or make it just basically 4,190 joules per kilogram per degree Celsius. So you can measure the temperature, how much it went up, and that is the change in temperature from what it was to the new temperature. To the difference between them is going to be delta T. So now you know how much heat went in, let's say in 5 minutes. Then you can measure H in this case, which is just simply Q over T. T is the time, in this case 5 minutes. So you know H. But in this case, the problem with finding H in here is that the geometry is not uniform. So it changes basically, at least the temperature at a given point is different than the temperature at different points. So at a point Y, basically, what we're saying in here is the temperature is going down from TH down to some TH plus DT, just enough for the next dy. Basically, this is y plus dy, the next point. The temperature is actually sitting at T. The reason why I'm saying this is because the temperature is definitely going down from T hot to T cold. Normally we take y to be at T and this point to be T plus dt, but if we do that, we have to make sure that dt is actually negative. Okay, that's the only thing, and usually we like to write the positive in here. So this is basically for this problem the way it's set up. And at some point, basically what we're saying in here, the heat that is going, which is constant and uniform, because we're reaching basically a point where this heat exchange is going at a constant rate, so is given by, for this section from this points only, from here to there, as being simply equal to K times the area. It's this area really that is of concern, which is pi r squared. Okay, so we need to find how r is related to y, because this is how far we are. Obviously pi, this is a radius of r2, this is a radius of r1, so the area decreases from a pi r2 squared, because r2 is bigger than r1, to pi r1 squared. So definitely the area is not constant, so I'm going to put it as pi times r squared times the change in temperature. Obviously the final temperature minus the initial temperature, I have a minus dt in here, and this is just to get the expression for H positive flowing from top to bottom, divided by the distance between these areas, basically here and there. So this length, the thickness of this side, to be dy. Obviously I'm taking dy so small that I ignore this inclination that I'm just taking the pi r squared as just being the area. So if you're curious about it, the area is slightly bigger on this side than the other one. But if I make dy so small, this will not matter. So it's one of the areas is fine. So this is basically what we're working with now. Remember, dt has a negative sign in it if I write it this way. If I put it up in here, it's going to be t going to t minus dt because we're going down. So in either case, we have to have a minus in here. Okay, so I needed to find that y as a function of r. And basically the way I proceeded was finding some angle in here and basically taking the tangent of that angle theta and working the algebra, and everything would have gone fine except that we made a mistake. I made a mistake, okay? So this length is L given from top to bottom, and I assumed that the overall length is some height h. So in this case, the tangent of theta is clearly equal to r2 over h, or is equal to little r, because this is r, that's the whole area, pi r squared, by the way. So little r over just this distance, which is simply h minus y. So it's little r divided by h minus y. Or finally, it's actually r1 divided by just this length, which is the h minus l. And this would have worked fine if I didn't do that mistake, okay? So the first and the last two terms give me a relationship for h, and we would be in business. That's where the mistake went, actually. So r2 over h is equal to r1 over h minus l, and this would have, if I flip the equation, basically it's going to be h over r2 is equal to h minus l over r1, okay? And if we're careful with the algebra, basically we move r1 to the other side and move h to this side. It's going to give me 1 minus l over h, which is equal to, basically from this equation, r1 over r2, okay? Manipulate this expression in here, move this term on this side and the other one on the other side. So basically what we end up with in this case is 1 minus r1 over r2 is equal to l over h, okay? And finally, this gives me an expression for h, and this is where it went wrong completely, okay? This is where the mistake was. It's L divided by this term, not multiplied. Okay? It's L divided by 1 minus R1 over R2, which is equal to R2 L over R2 minus R1, okay? So this is H. Now use either of the other two equations to find basically what R is, because we need R as a function of Y. So first equation basically tells me that R is equal to R over H minus Y. This is equal to, according to that equation, R2 over H, R2 over H. And R2 over H, if you can clearly see from this expression, where is it? Here. R2 over H. If I bring H to this expression, it's going to be R2 minus R1 divided by L. So this is actually R2. I'm sorry. Hold on. Let's not make another mistake in here, okay? R2 over H. From this expression, I know R2 is equal to, H is equal to R2L divided by R2 minus RL. So from here, R2 over H is the same thing as R2 minus R1 over L. So this is R2 minus R1 over L. So now R is equal to R2 minus R1 over L, that is this ratio, times H minus Y. Okay, and H is again that term in here, so everything should be fine now if we are careful enough and not to make any mistakes in the algebra. So R is equal to, again, R2 minus R1 over L. When you're doing problems like this one, it's a good idea to be methodic and to be systematic. Don't do too many steps at once. That is basically where the problems happen, like I did. So R2L over R2 minus R1 and then minus Y. Okay, so simplification. We have R2 minus R1, we have R2 minus R1. We have L, so this cancels, and we'll be left just with R2 in the first term. R2 minus, again, this coefficient, which is R2 minus R1 over L times Y. Okay, this expression should work now because of the fact that if I put y equal to 0, I know the radius is equal to r2. That's exactly how it's supposed to be. Okay, if I put y equals to 0, because I'm starting in here, this is what y equal to 0 look like, this is what y equals to l look like, and this is y anywhere in between. So for y equals to l, I know r is little r becomes big R1. So let's test that now. That is really where the check last time failed. So y equals to l, this gives me r equal to r2 minus, remember y is equal to l now, so l cancels the l, so it's going to be minus r2 minus r1, which is plus r1. These two cancel, and indeed it gives me r1. So this works. Okay, this expression is the correct one. There is another way of finding this expression that is probably a lot easier than what I did. Okay, and that is the following. We know this expression is linear because it looks like it's a line, and that's actually how the shape is, and that's how it triggers all of this rationale, actually, with the tangents and all. So what we're looking for is an expression of this following. It's like for the equation of line, except that now we have y and r, but we're looking for r as a function of y, not the other way around, not y as a function of r, because the expression has r in it. So this is what we're going to do. We know that the independent variable is going to be, in this case, y, and the dependent variable is going to be r. So this is linear of the form of a plus by. Okay, so this is another way of doing it. Okay, I mean the expression is correct now, but we want to arrive to the same expression with a different way. So what we're saying in here is this is an equation of a line. So we know that this line passes by when y is equal to 0, it passes by r2. We also, so this is an equation of r that plots basically r as the x-axis and y as the y-axis. Okay, so sorry, did I do it again? It's the other way around. It's y is in the x-axis and r is in the y-axis. The independent variable is r. The dependent variable is r, and the independent variable is y. So again, for y equals to l, we know that the radius is equal to r1. So let's plug in and find this to a and b. So we plug in for y equal to 0, so we have 0 times b plus a. This must be equal to r2. From here, clearly that a is equal to r2. Okay? So we get one term, which is the little a. We do the same thing for b by plugging y equals to l and find and require that this must be equal to r1. So we have r1 equals to, we know a now, which is r2, plus b times L. So from here we can find the b equals to, okay, I'm going to move r1 to this side, and I'm going to move this one to the other side. It's going to have a negative, so it's going to be minus divided by L of basically the difference r2 minus r1. This is simple algebra that I hope you guys can clearly get through it. But the point being in here is that I recover the same expression in the sense that y equals to r2 minus r2 minus r1 over L times y, which is what I really wanted to find last time around. Okay, y, I'm sorry, why is it y? This is r actually. This is what we want, okay? R, the radius, as a function of the height, okay? Which is exactly how it's supposed to be. So now we have that, okay? Either way, you can convince yourself it's either this approach, which is a lot easier, or this business of working out with basically the geometrical method, and at the end you end up with the same expression. Okay, r2 minus r1 over L times y. Okay, and this of course satisfies these conditions because we started with them. Okay, and so now let's go and finish this problem. Okay, so we have h equal to minus k times pi times this r squared times dt over dy. Okay, remember r is a function of this number. As a matter of fact, I need to find what dy is in terms of dr, because instead of varying y from 0 to L, I'm going to vary r from r2 down to r1. Okay, that's it, and the integration should be the same. And the temperature, of course, changes from T hot down to T cold. Okay, so that is basically the setup of a problem. If you look at it on top, y changes from 0 to L, the temperature goes from T hot to T cold, and the radius goes from R2 down to R1. So that is basically the integrations. So what I'm going to do is integrate over r instead of over y. So I'm going to do this change of variable, which is already available for me. So that means that dr is equal to minus r2 minus r1 over L times dy. In other words, dy is equal to minus L over r2 minus r1 times dr. So making that substitution in here, I have the minus and the minus, they will cancel, so we'll have a positive in there. So it's going to be h equal to k pi r squared. So this is a positive because there is another minus coming from that term in there. And the reason why I want it this way is because r2 is bigger than r1, so I know it's positive in here. That's why when I was doing the algebra in here, where is it? At some point I made this change, not the other way around, because I know r2 is bigger than r1. Okay? So in this case, times dt divided by that bunch of stuff in dr. So times L divided by r2 minus r1 times dt over dr. Okay? Obviously, I need to separate these variables in here and move the stuff with the dt on one side and integrate over t from t hot to t cold, and integrate r from basically r2 to r1, and we have found the answer to this problem. So let's do that. So what we have in here, we have h times dr times r2 minus r1, okay, divided by k times pi times r squared. So all of this stuff is just this term multiplied by h, of course, divided by L, of course, divided by k pi r squared L. Remember, I have dr and dr squared in the denominator is equal to dt, basically. So just move things around until you get things to where they need to be. R2 minus R1 and H and K pi, pi and L, they are all constant. H is constant for the fact that we'll have the heat current is constant because it's going at a constant rate. So everything else is constant with the exception of R and T. So the integration from T hot to T cold of dt is equal to, again, H times R2 minus R1 divided by K pi L, the integration from R2 to R1 of dr over r squared. The integration, the antiderivative of 1 over r squared is negative 1 over r, and this will simply be equal to minus h. This on this side it's tc minus th. Okay. On this side it's going to be minus r2 minus r1 divided by k times pi times L times, again, 1 over r1 minus 1 over r2. Okay. Obviously, there is some algebra in here. This minus, I'm going to move it to the other side, and it becomes a positive number because th minus tc is positive. And in here, it's going to be h times r2 minus r1 over k times pi times L times, again, I need to get this common denominator, which is just r1 times r2, and in the numerator it's going to be r2. Okay, there is another mistake somewhere in here because this is not correct. Okay, did I do it in here? I think the dr it looks like it's correct up to this point. Man, I hate these things. Okay, dy in the denominator. So why did it move in the numerator? See, dy is minus L over R2 minus R1. So this is actually backward. So this should be R2 minus R1, and this should be L. Because remember, dy is equal to that number. So for some reason, I flipped this thing in here. Okay, it's L dr, not R2 minus R1 times dr. So there is a mistake in here. It's subbing this value. Hopefully you guys caught it. Okay. So again, it's going to have in here, this term is going to be actually R2 minus R1, and this term is going to be L. Again, these are not scripted. So hopefully you guys appreciate the fact that this thing is live, and the fact that you need to work these problems regardless of what you do. Okay? Again, times L. So all of these terms in here, the H and the L move to the, the L and the term, the difference between them. So this will become R2 minus R1, and this will become L. So the reason why I know that is because at the end we're going to get into H, and it should be inversely proportional to L, and we're getting it proportional to L, and that is nonsense. If L stayed in the denominator, that means the longer your this plug, the more heat is going to transfer, and that is nonsense, because if you want to insulate an object, just make the walls thicker. So that's why I know that it's leading to some nonsense result. Okay, so that's how you think about your problems you're solving. Now it looks like we're in business. R2 minus R1 cancel. Okay, and we have in the expression now. Let's clean it up a little. So it looks like it's TH minus TC is equal to H times L. Now the H will be inversely proportional to L if I really find the H, which we are going to do soon, which is K times pi times the product of the two radii, the inner and the outer. And now we have the expression that we were looking for. As a matter of fact, we can find H from this expression, because that's what we were asked to find it for this material. It's going to be K proportional to K times pi, which is typically for the area, times the product of the two radii, times, it's not an area, it's really like an average of the two areas, the bottom one and the upper one, because the lower area is pi r1 squared, r2 squared, and the upper one is pi r1 squared, and this is somewhere in between them, which is just pi times r1 times r2. In other words, it reduces to one of them if this all of a sudden becomes a cylinder of radius one or the other. Okay, so in other words, if r1 is equal to r2, we get back the old result that we know. Okay, times, of course, the difference in temperature between the outer and the inner divided by the length in this case. Exactly how it's supposed to work. Okay, if I continued with this expression, at some point we were going to find the length in the numerator. That means the rate will grow with longer and longer plug, or bigger and thicker and thicker wall, and that is nonsense. That is non-physical. So this is how you find your mistakes, and I'm glad that these mistakes happen, and I'm hoping that it's going to be a learning thing for you guys. So this is part of a homework problem actually, and I'm hoping that you guys did not struggle as I did with solving it, especially with the algebra, because again, we need to be focused when we're solving problems as much as possible. And the biggest thing is, making a mistake is natural. Everybody does. Whoever says he doesn't do a mistake is exaggerating, and it's not true. It's a lie. Okay. As a matter of fact, this is not me saying so. Actually, big physicists, they say that, and they admit that. Humility is part of your job, part of what you do as a scientist. Okay. That is natural, and this is actually, everybody says that, okay, including Einstein himself and everybody else who is supposed to be the most genius people. So that is natural. So do not think yourself that somehow I am kind of not good at this thing, so therefore no, that is natural. Catching the mistake though and fixing it, that is a skill that you need to learn. Okay, that you're going to take with you in your workplace or wherever you do. Okay, thank you guys.